Recording
Hey
in
everybody,
progress.
welcome back. It is Tuesday, September 13th. We're getting ready to finish up Chapter 3 in Statistics. Welcome, Clayton. Today we're doing 3.4 and 3.5. So we'll start with 3.4. 3.4 is on measures of position and outliers. And outliers. So before we do that, well, part of it, let's talk about the empirical rule again. I need to do this several times this semester, make sure you guys see it repeatedly. The empirical rule is related to a bell curve. That's not too bad. That'll work. In the middle, we have the mean, which goes by mu for a population, or for a sample, it's x bar. And then we put out hashtags in three directions. Well, two directions, three hashtags in each direction. So I'll do one there and one there. Let's see, will green show up? We got red and green. So going over one deviation, these are steps in deviation, which is sigma or S. Sigma is for populations, S is for samples. We go over here, this is mu plus 1 sigma. Over here, this is mu minus 1 sigma. These are just numbers, so once we plug in the numbers, they don't look like these crazy number characters. They're just numbers. So I will use, I'll show you the IQ one, and then we'll talk about some other ones. Let's see, if we go over another one, this is mu minus 2 sigma and mu plus 2 sigma. Finally, our green one is at mu minus 3 sigma and plus 3 sigma. So I'm going to put these down below. Mu and x bar. So this, if I draw it well, looks symmetrical or like mirror images on each half. Maybe I haven't done a great job after all. Put a little bit more towards the center. And I'll make little dash marks for the other ones, because there are cutoff values here. When we go one deviation away in either direction, like this side over here or this side over here, each side contains 34% of the total data. If we go one deviation away, which is a total of 68%, we add it up. Then if we go one more over, there is 13.5% of the data in these sections. Lastly, we have Well, not lastly, there is one more section. We have 2.35% here and here. And in the final regions, we have 0.15%. So those are the numbers for each category. If we go within one deviation of either direction, it's 68%. If I add 13.5 and 13.5, that's 27. If I add that 27 to the 68, we have going within two deviations is 95%. And if we go all the way out to three deviations, this covers 99.7% of the data or the results. That's when I say data, it represents pictorially, it's the area under the curve pictorially. In terms of data, it was the values. We showed that last week when we had like 200 on the screen and we had a bunch selected based on height or weight, I think we were doing. These values are important. You'll see the 68, 95, 99.7 a lot. And this is, how do I put this? This is an approximation. That works because it's easy to remember. Like the real value isn't 95. 95 in reality is like more like 95.4. Really, I think that's it. How do I know? I don't remember because we don't use that. We will see it digitally. Ooh, about to lose my graph. There we go. So, so it's an approximation. Exact results we get when we do it in the computer, you'll see. I want to give you some examples that are known when we do IQ. The IQ test has a mean of 100. Let me do this up top. IQ is mean of 100, standard deviation of 15. That means the mean is right here. Oh shit, I roasted it. Well, yeah, I don't need the 68%. This is the value 100 right here. This is the average score we get. If I add 15 to get over to here, 100 plus 15 gives me 115 right here. And I add another 15, I get 130 right here. And finally, I add another 15 and I get 145 right here. If I subtract 15 from 100, I get 85. That's not in line with the rest. 85. 85 minus 15 is 70. And 70 minus 15 is 55. So these are the values you'll see on the IQ test. And what is it called? It's the Stanford-Binet test, I think. Yeah, I used to have the website. I used to have the website written down. Let's see if I can find it. Let's go look for the IQ test real quick. Bring that back in a second. Stanford-Binet test.com. Yeah, the Stanford-Binet. It's Stanford-Binet test, and it's with the way they gauge IQ. You can do a quick test, a full test, and it's when you hear they've got an IQ of so and so. That this is what they're talking about. This test right here, the Stanford-Binet test. IQ for a genius is, I believe, 142. Some fun stuff to look up if you ever wanted to know. What I want to use it in this class, the examples I want to use real quick are height. Most people don't know their IQ, and if they do, they don't want to share it. So let's take a look at height. Let's see, the male average height is 70 inches. And there's a standard deviation of 4 inches. So adding 4 is pretty easy. I can do that, and I can subtract 4 pretty easy also. Now I am 5'5.5". The 5 feet is 5 feet turns into, you multiply by 12 to get the inches. It's 60 inches, and then I have another 5.5. I am at 65.5 inches. So I lie here on the bell curve, right below 1 deviation out. That's El Jefe right there. And this is for males. So males have 70 for the mean, and standard deviation is 4. For females, the mean is 65, and the standard deviation is 3.5. In general, women tend to be a little bit shorter than men. Would it be fair for me to try to compare myself to another woman that's 60 or 65.5 inches? If we're going directly in terms of height, yes. But if we're trying to see who represents the population more accurately, no. I'm at least 1 deviation out. A female that is 65.5. I'll put the female row right here. The female had 65 here, or yeah, 65 there, 68.5 here, and subtract 3.5 would give me 61.5, and I can keep going. Another 3.5 gets me down to 58, and another 3.5 gets me down to 54.5. Adding the other way gets me to 72 and 75.5. So a female that this is this height, that is 65.5, is right about here. So a female my height is taller than the average female. So, oh, I'm off screen.
I have a question.
Yeah.
Um, for the males, I don't know if I just didn't hear it, but like, how'd you get to 4? Like, how'd you know to go up by 4?
It's the standard deviation. This was something I looked up a while ago. It might have even changed by now, but rather than changing my lecture notes every semester, I'm just keeping them consistent. This is, if you Google it, sometimes it will do individual countries. This might be for people in America,
Okay.
people across the globe. I think it's a little bit different. It's a little harder to compare. Some people in certain regions are taller in that area. Uh,
Okay. And so for like an actual like problem that like we get on like the midterm or something, like how would we know like
they will give you the mean and the standard deviation.
oh okay. Okay. I just wanted to make sure because I
Yeah,
didn't know
that's a
if you did
great
anything.
question.
Okay. Awesome. Thank you.
Yeah, yeah, you can't, if you don't have the information, you can't do this. This leads to statisticians deciding, well, maybe comparing our actual scores isn't a good idea. When I say score in this category, I'm saying height. So what we've come up with is, does anyone need this up longer? I'll pull it back out in a second to reference the picture. Uh, but what we've come up with is called the z-score. Nope, that's not how I wanted it. There we go. Tinker with my camera right at the last minute is not a good idea. Okay, so z-score. It allows us to compare apples and oranges, or things in two different groups that have different means and standard deviations. I already showed you what someone that was 65.5 in terms of female. So let me give you one that we may not know. So I'm going to say Jones is 65.5. And I had a TA for the last class I taught in person. Her name was Brooke. She might even still be TAing at COS. She was 4'11", which translates to 59 inches. So, like, that's definitely shorter than the average female, which was 65. I'm shorter than the average male, which is 70. Who was shorter relative to their groups? When we do z-score, we use, it comes from the whole mu plus sigma, we could do 1 sigma, 2 sigma, 3 sigma. So when we don't know how many sigmas, what we call it is z sigma. And if I take the mean and multiply it by this multiplier, z times that sigma, I can get the individual score of an individual user. So like my x, this is my x score, and this is her x score. So the way they get the z-score process is they subtract the mean from both sides, and that gives us z sigma. And then they divide both sides by sigma, which just leaves z on the right, and we get the formula for z-score. Z equals x minus mu over sigma. So that's what we're going to use to calculate z-scores. And then we can compare myself to Brooke. So I'm going to get this out of the way. This is just the derivation. You don't need to know that. The z-score is what you need to remember. So let's calculate the z-scores for each group. I will use red for me. For red, Jones, my x score is 65.5. The mean was 70 and standard deviation was 4 for males. So if I plug these in, I have z equals 65.5 minus 70 over 4. And I do the subtraction first. I get negative 4.5 over 4. Which is negative 1.5 over 4 is like 1/8, 12.5, 1.25, 1.25. I didn't put the negative in, so whatever I have is going to be the negative answer. Yeah, 1.25. That's my z-score. I'll show that on that picture in a second. Let's do Brooks as well. Brooks category, she had 59. The mean was 65, and standard deviation was 3.5. So when I plug that in here to this formula up here, I have 65. Oh, sorry, 59. 59 minus 65 over 3.5. I do the subtraction first. 59 minus 65 is negative 6 over 3.5. And that is about negative 1.7. I'll do as many decimal places as I had up there just to match up. So I'll give you like 30 seconds to write that down. We'll bring back the picture and illustrate what the z-scores are here. If you need that up longer, let me know.
Yeah, can you go back to that page?
Yep. I thought I might be racing, going a little too fast.
Thank you.
Yep. Okay, so the z-score table has the same thing here, but for z-scores, the mean is 0 and standard deviation is 1, which makes the z-score look like a number line. We have 0 in the center, and we just count 1 as we go to the right, and we just subtract 1 as we go to the left. So these are z's. And David is still here. My negative 1.125 is right about there. And we had negative 1.7, which is closer to negative 2 than negative 1. It's further over here. So that's negative 1.714 for Brooke. So I am closer to the average for my gender than Brooke is. David is closer to the average male height than Brooke is for females. Oh, I'm off the screen. Now, unfortunately, there is no way to do this for non-binary. If we do the full spectrum of stuff like genetically, how much of a male traits has someone picked up in their genes versus female traits, there's no way of doing that. This is all based on what genitalia you have at birth. There's no other way for them to do it, and so this does not. If you identify as non-binary, this is based on birth and isn't the most accurate thing, but who really fixates on height? Unless you're like a basketball player or a jockey, a racing jockey, height's really not all that important. But that's how we calculate z-scores, and that's how we can compare things of different categories. Where do outliers fit in here? I started with this talk with outliers. So let me show you outliers. We talked about outliers before, how they make things, some traits or some statistics are resistant and some are not. In terms of the empirical rule, outliers are past the 2 mark. Well, now I want to center where I wrote outliers. It's bothering me. So it's more than 2 deviations away. More than positive 2, less than negative 2. That puts it in the outer 5%. We bring this down where you can see the percentages a little bit better. These two categories right here, 2.35 plus 0.15, makes 2.5% here. And we have the same thing going on over here on the left. 2.5% is past -2. And adding those together gets us 5. So outliers are more than 2 deviations away from the mean. And we consider this unusual. Outliers are unusual. Not every bell curve has stuff in this -2 and past 2 range. Sometimes everything's just right there within this range right here. It's just not everything has an unusual category. So unusual in statistics, unusual is less than 5%. And when I turn that to a decimal, you'll see less than 0.5, 0.05, sorry, probability. We haven't studied probability yet. That's coming in chapter 5, which we're doing Thursday, we're starting. But I'm hitting this unusual early and trying to get it to you guys. Hit it repeatedly. If you take the social science set when you're doing in social sciences, stuff like that, social sciences use M for mean rather than mu and sigma. They do their own thing, so it's a little confusing comparing them across groups. And I'll pause and let you guys soak that up. Does anyone need this up longer? Okay. Slide it up. There we go. So we've been doing this bell curve. Or it's the picture we use in the empirical rule, which I just had up. We use this a lot for things that are regular, like regular distributions. And the figures, the things that it's good for is using the mean and standard deviation. So X bar and S for samples, mu and sigma for populations. When we have distributions that are irregular, like skewed graphs, both skewed left and skewed right, we don't like to use mean and standard deviation because it's not really reflective of the center values and stuff like that. So for skewed graphs, we like to use the median as our center, just like mu and sigma are for bell curves. And then we like to use IQR, which stands for interquartile range. And we like to use this for measures of dispersion. I did this funny. The mu and x bar are center. The sigma and s are the measures of dispersion. It's called interquartile range. It's something StatCrunch does, and we'll show you that in a little bit. What the IQR does, the IQR's value is Q3 minus Q1. And you're like, what the hell is that? I'll show you. So when we have data, if I don't put the bell curve up there, I'm not even going to put the any type of graph. I'm just going to show like data sets. If I have a number line, and let's say the lowest score is right here, and the highest score is right there. Halfway between is the 50% mark. 50% is the median. And then I go half of the way between 50%. This is 25%. And this is 75%. If I go halfway, it's adding 25 either direction. Low, we're going to say 0%. And high is 100%. And so what these percentages are, these are called the percentiles. And what the percentiles show is the percentage, whatever your percentile is, the percentage of scores that are below yours. Or whatever, if it's not yours, the figure that you're looking at. There. So if you've taken the SAT, like when you were in high school, if you took the SAT measures in percentiles. The reason why they do this is because each variant of the test that they give out, it's hard to say is this test is equally as difficult as the next test or the previous test. So what they do is they do it of the percentile is the of the people that took the exact variant of your the SAT test that you took. So like let's say there's a 1,000 different variations of the SAT test and you took 777 test 777. They will take every other student that has taken test 777 and your percentile is calculated from there. They don't include students that took test 776, 778, or any of the other thousands, just the ones you took. That way they can compare apples to apples more fairly. Because it's hard to show via tests. What does it? The GRE, the Graduation Requirement Exam, if you want to go to grad school, does the same thing. Some subjects have specialized scores or specialized tests. Like there is a GRE for the math exam, GRE math. That's what I took when I went into grad school. I didn't need to take the regular GRE. They only cared how good I was in mathematics. Uh, guess what my percentile was? Let me give you an example on the SAT what a good score is. If you are in the 95 percentile, what it means is 95% of the people did worse than you, only 5% did better. So if you get like a 99 on the SAT, you're like in the top 1% of the people that take the SAT. So in terms of math exams, Jones's score was in the 60s. Not very good, just a little bit above average. The math exam has a lot of stuff that's got theoretical or pure mathematics. This is me justifying why I got such a terrible score. Mathematics and a bunch from applied mathematics. The school I went to only did applied mathematics. That's what my degree is in, applied mathematics. So every problem that asks something from the pure math side, the courses that I didn't take, there are things like abstract algebra, number theory. There's a bunch of categories. I had no idea. So I scored that, but I still got into almost every single grad school I applied for because they thought that was pretty good. Apparently, very few people actually, I don't know if these percentiles are very good, at least on the GRE math exam, because I got into where I wanted to go with, like, I think it was like 65 or 66. Uh, but those types of tests do it. Let's get back to what we're talking about. Those were just examples, the SAT and the GRE. What do the quartiles do? So we call this one, well, like the low is like effectively Q0. And each one of these hash marks represents another quartile. Quartile is like quarter. Is like quarter. And if you think about money, a quarter is 25 cents. Quarter is 25 cents. Or another way to look at it, a quarter is it's 25% of a dollar. And it comes from doing 1/4 or 1/4. So that's how we've labeled them. In fact, generally you don't see Q0 or Q4. They just call them the low and the high scores. Very rarely do you see Q2. Q2 is called the median. So this is for skewed data. And to use it, we really have to, data must be sorted from low to high. which is a pain to do when there's 20. It's mind-breakingly mind-numbing to do when there's 1,000. This is not something you want to do generally by hand. Let me leave that up while I'm erasing the other one so you guys can write down. We're going to use that for more stuff in a second and give some examples. Does anyone need that up still? I've got it here on the side if we need it again. Can I do this sideways and still get it all in? Not really. So we'll go back to the variation we have it set up as. So I'm going to redraw those for a second. So we have our median here. Median in stats, we use M for median. This is Q1, Q3. Rather than saying high, we call it the max. And rather than saying low, we call it the min or minimum. And so we need something that is the equivalent of the outlier, like the 5% thing on the outliers. And so the way we find the equivalent here are called the fences. There is a lower fence and there is an upper fence. Both of them require using the IQR. So both use IQR. Which, as a reminder, is Q3 minus Q1. So what they do to get the lower fence is they take the Q1 value. It's a number, remember, these are all numbers along here. They take the Q1 value and they subtract 1.5 times the IQR. And to find the upper fence, maybe I'll do this one with green. They take Q3 and they add 1.5 times the IQR. This ends up having two outcomes. Let me kind of like, well, two outcomes for either fence. Let me just give some examples. That's like skewed left. And something that's skewed right, sorry. Something that's skewed right, but maybe isn't skewed as much looking is like this. So in two scenarios can happen. Either I'll just focus on the lower quartile for now, or the lower fence, which I usually abbreviate LF. The lower fence can either be outside the min, can be lower than it. So that's like option A. And option B, the lower fence is inside or above the min. And really, if you picture it as a fence, like let's say our house is right here. This is our house. And we have a yard. And we have a fence. If all of my lawn or all of my pets, let's say, all my pets are inside the fence, none of them lie outside the fence. But if my fence is here, like say my lower fence is right here, and I've got a couple animals outside, like right here and right here. Ooh, orange is crappy. If there's data outside that fence, those are called outliers. And the same thing happens with the upper fence. I could have the upper fence be outside our data range, or I could have it be inside the data range. If it's inside the data range, anything past that line is an outlier. Same thing with the lower fence. If it's inside the data range, anything past that lower fence going downward is an outlier. And I think this is a little easier to see when we do it with numbers and show it graphically. When the more skewed a graph is, the more it's likely to have an outlier. This picture might have an upper fence right here. Whereas this picture, the upper fence is probably here. A little bit higher. That's just pictorially what we're doing. I think showing it will help.
Okay, I have a question.
Yeah.
To me, looking at your paper, like it just looks like there's like a bunch of like, it just looks like gibberish. Like I don't understand like any of it really. Like, like the lower fence part, like the minus 1.5.
These are calculations. These are calculations. The lower fence and upper fence are calculations that the computer will do for you. I'll show you how to do it by hand. But without actual data, it's a little bit more gibberishy. I agree. So I'm just waiting for everyone to be finished, and I'll show you examples.
Oh, okay.
Without,
Okay, yeah, because yeah,
yeah,
it
I
just looks like
agree. It's a little hand wavy right here.
yeah.
You don't even need the pictures so much. You'll see it when I do data right here. You don't really need this. I will show this with data in a second.
All right, cool.
And I'll show you how to do the calculations for it too.
Okay, cool.
So let's take a look at some examples. Does anyone need that up on the screen for a little bit longer, or can I switch over to StatCrunch? I hear no arguments. Let's see, I'm going to load from my data. We'll pull up a data set that we had, the project. And so, what's a good one to use here? Do I have siblings on this category? No, I don't. So we will use, let's find a graph that's skewed. Why, okay, age is on there. Let's just take a look at all of these graphs and see what they look like. So age is skewed, that'll work. Shoe size really isn't. Frequency, or the height is fucked up for people that entered feet rather than inches, so I won't use that. So let's take a look at age and shoe size. So I'm going to pull up the summary stats for those two groups. I'll do age and shoe size. And the ones I want to look at are, I am going to do the minimum. I'm going to put these in order like they are on the bar graph that we had earlier. Q1, the median, Q3, and the max. And I told you we need IQR. IQR is on the list. I'll add it, even though I'm going to show you how to calculate it by hand. So, let's see. Shrinky-dink that thing down. Move this over here where I can access it. And hopefully, yes, there we go. Have both up. So making this graph, if I were to do this by hand, I could put in these numbers right here. And this, I'm going to do the age line right here real quick. So the median is 21. Maybe putting the min and max up here first helps. The min is 14. That's my min. If I put up the max, it's 79. We'll put that right there. I've got the median is at 21, which is really close to 14, right? Q1 is at 18. Look at that. I can't even write it below. And Q3 is at 32, which is 32 is 11 away from 21. 14 is 7 away. Q3 is further away from the median than Q1 is. So this is 32. And this was our Q1, median, Q2, or Q3, and max. So this is for the age data. And it's telling me the IQR is 14. So the computer says IQR is 14. Where are they getting this from? What they are doing is they're taking this value, which represents Q3, and this value, which represents Q1, and subtracting. 32 minus 18 is 14. Now, where are these fences? Where is this fence talk? Both things use 1.5 times the fence. So I'm just going to calculate that real quick. .5 times IQR is 1.5 times 14. And if you do that in a calculator, you're going to get 21. So how do they find the fences? What they're going to do for the lower fence, we're going to use this 21 for both of them. The lower fence is going to do Q1 minus 1.5 IQR. Q1 was 18 minus 21. 1.5 times the IQR. And the lower fence is at negative 3, which is way over here to the left. Lower fence is negative 3. Clearly, we can't even get someone that age. You can't be negative years young. If we look at the upper fence, it's Q3 plus 1.5 IQR. In this case, the Q3 is 32. And we're going to add 21. 32 plus 21 is 53. 53 is about here. The upper fence is 53. This is the whole scenario of the call is coming from inside the house. We have outliers. So any data score greater than 53 are outliers. Does StatCrunch show this graphically? Do they have a nice handy graph? Yes, they do. While you're writing that down, I'm going to erase my other board and show you how to get it. Which is the topic for 3.5. So we're moving right along.
Can I see how you got that data on the StatCrunch?
What do you mean? How I calculated it?
Yeah.
Stats, summary stats, columns. Most of the
Oh, okay.
ways we'll find summary statistics for groups of data is going to be doing this same thing almost every single time. Stats, summary stats, and columns will be finding results for an individual data group. We've got a wide range of stuff we can choose from. But I will write that over here on this other whiteboard.
Awesome. Thank you.
Does anyone need this up long? This picture? Oh shit, the picture's not up any longer. Does anyone need the picture up longer?
Yes.
Okay.
Thank you.
Before I do it, the graph, I'm going to go over here and I'm going to sort the data table by age. Let's sort all columns by age. And I'm going to do descending because I'm looking for those older people. So I'll put the higher numbers on top. And let's see. We said anyone above 53. What are you doing? Stop that. That column has age 79. This column has age 57. This column's age 52, so it's underneath the fence. So we've got 7 pieces of data. 7 data members that are going to be outliers. So let's show how to see all this stuff kind of graphically in StatCrunch. So finding, oh, I'm still off the screen. Finding min, Q1, median, Q3, and max. In StatCrunch, You're going to go stats, summary stats. And you should have your stuff sorted in columns. You select the column. Step 1, select the column that has the data. Step 2, select the summary stats that you want in the box. In this case, min, Q1, median, Q3, and max. And I recommend you do them in order, because otherwise you're going to, if you don't do them in, like the order I have here, not the order they show up in StatCrunch. I'll show you what that looks like in a second. If you put them in that, put them in this order, this is how you can use it. And this, to be honest, these five numbers are called the 5-number summary. They summarize the data using 5 numbers. To find the graphs, to find a visual representation, we're going to go, of course, in StatCrunch. We're going to go graphs, Boxplot. I hear the air fryer going. My wife is heating up food, that dirty little rascally wabbit. Right? That's the trade-off for doing this 6:30 to 8:30, Natalie. If you don't eat dinner beforehand, you're like, fuck, I want to eat.
Yeah, but normally I'm not hungry enough to have dinner beforehand, but then midway through, I'm hungry.
The reason why I do it now is I don't want it to be too late, but this makes it so people that have day jobs and stuff like that can still attend a lecture that's convenient for them. Why the hell did I make the P capital? That looks crazy. There we go. That made it look like representation, not representation. Are you guys good with this for now? Can I do it in the StatCrunch? All right, if you need it up longer, let me know. I'll put it back up. We're going to go graph, box plot. I'm going to tell it age. And you kind of want to make it say, you definitely want use fences to identify outliers. And you want to say draw boxes horizontally, because this is how you're going to see it in most things. Most reports you read it in, homework assignments, anything like that, they draw them horizontally because a vertical box plot just takes up too much page space. Oh, what are dividers? I'll have to play with that in a second. That's all you gotta do is click these 2 boxes. I'll write it on the list in a second. And look at this little box plot we get. If I put my cursor over it, it gives me all the important data things we need. The lower limit, which is the minimum, is 14. It says Q1 is 18. Q2, the median, is 21. Q3 is 32. It's giving me upper limit is 52. Did I do something crazy in my calculations? Why are they saying lower limit is not the lower fence? It's the minimum value. So they just went with minimum value. They're saying anything above 52. I'm not sure why. That's off. But that represents these lines right here. Like this line right here in the blue box, that's the median. This left line is Q1. This right line is Q3. These vertical lines right here are the fences. And so notice I got a bunch of pink dots to the right. If I put my cursor over it, it will tell me exactly where they are and what the age is. So I got a 57, I got a 58, I got a 61. I got two 61s. It can't show two dots there though. I've got 63, 65, and 79. So these are the outliers right here.
Did you select something differently so that it could show you the outliers on the graph?
Say that again?
Did you select something like on your options so that you can see the outliers on the graph?
Yeah, I'll bring it back up. You click, well, no, the fences show up automatically. Like when I started it, this is what it looked like. Let me do it from scratch. Finish putting that back up. Shit. There we go. I will do it again from scratch and show you what it looks like without that. If I turn that off and I leave it horizontal, what does it look like? Oh, it's like, dude, pick a column. So here they still show the outliers, but they don't show where the fence is. So they just show the max and the minimum. And if I do this horizontally, if I put that in, but say horizontally, it does high on top. Nope. Yeah, it does high on top and low on bottom. And this can be really long and take up a lot of page space, whereas this can be relatively flat. If I were to copy and paste it, I could make the box look like this without squishing any of the like meaning out of it. Let me get rid of that annotation. So I can make this small and fit it on a report pretty well. This one, if I try to do the same thing, it just looks like shit. So you kind of want to do them horizontally. So let me bring up that thing real quick. We'll make a note of that here. Make sure to click if it's not. It should come clicked already. Click use fences for outliers on. So click on. I guess I should do it like that. That's the first thing we want to do, and we want to do horizontal box plots. I'm going to show you how to do this by hand. I think it helps with the comprehension. Just looking at the graph doesn't really help a lot. I mean, it gives you some, but until you've made the graph once by hand yourself, at least one of them, it's less meaningful. It really is. Notice that the graph. Oh, I don't want that one. Let's get rid of that one real quick. Put this back over here, and I'll put the text back up so you can write it. Notice I don't have any outliers to the left. This data is a skewed data set. Generally, on skewed data sets, the outliers are only in the direction of the skew. So this graph is skewed right, and that's where the outliers are on the right. You guys want to see how to do this by hand? Does anyone need this up longer? So let's come over here and do it right here. And I'm going to move all this shit to the top. Okay, so our box plot by hand. What we need is you need the 5-number summary. Which, as a reminder, is min, Q1, median, Q3, and max. And you need the IQR, but it is something you can calculate with them, with these numbers. So I'll list IQR as something useful if you're graphing it by hand. But it is calculatable. Remember, it's Q3 minus Q1. So when you have the 5 numbers, first thing you do is find the fences. The lower fence is Q1 minus 1.5 IQR. The upper fence is Q3 plus 1.5 IQR. And that's the only calculations you really need to make. The rest comes down to drawing it. So I am going to list the results from age that we calculated right here. No, let's do shoe size. You already know you already know what the graph looks like for age. Let's do shoe size. Let's see. We'll make the box plot afterwards. Let's see how well our box plot that we graph by hand matches what we have. So for min, I have 3.5. Q1 is 7.5. The median is 9. Q3 is 10.5. Max is 16. And IQR, the one that's slightly different, that is we can calculate ourselves, but they've done for us, is 3. So this is our shoe size data set. We're going to find our lower fences here, and then we'll graph. The lower fence is Q1, which is 7.5, minus 1.5 times the IQR, which is 3. So you can do this all in the calculator at once. $7.5 minus 1.5 times 3. And the answer is 3. 1.5 times the IQR is 4.5. If you calculate this separately, there's a benefit to it if you just do that once. You don't need to do the calculator or his work as much each time. You just use 7.5 minus 4.5. And then our upper fence is Q3. Q3 was 10.5 plus that 1.5 IQR, or 1.5 times 3, which is this 4.5. If I hit plus 10.5 here, I have both, and my upper fence is at 15. We have everything we need to do the box plot. I'll pause and make sure you've got that all written down before we start drawing it. Everyone ready? Everything we need is right there. So I'm going to make a number line. What you want to do is you want to start off and you want to do the minimum first. And give yourself some room on the left in case there's outliers. And you want to do the max on the right. And again, give yourself some room for some outliers. Ideally, it helps to know about how far this is. 16 minus 3.5 is pretty close to 16 minus 4. So that you don't, this is just to help you do the next hashtag marks. 16 minus, I'm going to round this to 4. 16 minus 4 is 12. I should have 12 values in between here. So I can do the midpoint. I don't need to do the midpoint in there. Yeah. The midpoint would be 12 divided by 2 is 6. If I come down 6, halfway, I can visually see about halfway. That's about 16 minus 6 is 10. And it looks like half again would be 3. So the quarter marks would be 6 divided by 2 is 3. So I could put a mark right here at 13 and a mark right here at 7. That's just going to help me to design my box a little bit better. So what I did is I did 16 minus this midpoint to get the 10 in the middle. And then I divided this value in 2. And what I did from the midpoint is I did the mid plus 3 and the mid minus 3 to show the other two. You're not going to have to do this by hand on the midterm, but it is handy to know how to do it. Let's label our values on this line. My min is right here. My Q1 is 7.5, which is, let's say right there. My median is 9, which is right about there. My Q3 is 10.5, which is right about there. And my max is 16. Max is over here. I'll put my fences in now. My lower fence that I calculated was right here. And my upper fence was at 15, which is right about here. Maybe I'll write this Q1, M, and Q3 down here. I think I want to use above this for the picture. And I'll write lower fence in and upper fence down there as well. So we got our max, we got our min, and we've got our lower fence, and we've got our upper fence. So the box goes between Q1 and Q3. Maybe I should pause, make sure everyone's got their number line. If you're taking the notes, the next part is where we're actually doing the graph. Give you a second on this. Okay, is everyone ready? So where Q1 and Q3 is, I'm going to make a box. And where the median is, I'm going to put a vertical line in that box. So what am I doing here? I'll write the instructions down here. Vertical lines at Q1, median, and Q3. And make a box. Okay. Then you pencil in the fences as lines. And you connect them to the box. Vertical lines for fences. And draw a horizontal line connecting it to the box. In my picture, it looks like the right side is a little bit longer than the left. These are called the whiskers. And they obviously come from a pet's face. You got your nose and the whiskers stick out. They're called the whiskers. So once in a while in old stuff, you'll see whisker Boxplot. And then finally, we put in, let me get rid of the word whiskers there. I can write that down below. These are the whiskers. And finally, if we have values outside the fence, put a dot there. I know of at least one value on the outside of the fence is at 16. There might be more. I didn't sort the data and look at it, but before I draw it, I'm going to sort it and look at it, or before I do the graph box plot, I'm going to see if there's more dots. That's it. This is how to draw a box plot by hand. Oh, plot as asterisks any outliers. So you have written instructions on how to do it too. But if you do it once or twice by hand, it kind of locks in the meaning of it a little bit more. It's more easy. It's easy to remember what the box represents, what the whiskers represents, what the stars represents, or the dots. I think it's easier if you just do a couple of these by hand. I can't make you do it on the homework. No one on the homework is going to make you do it. But if there's small enough value, I recommend doing it before you do if it asks for a box plot. I recommend trying to graph it by hand. Give yourself a little bit of practice with it. And I'll leave that up a little bit longer because I'm about to go back to the computer and it will hog up the whole screen. Start clearing my other board. We don't have too much more after this. I do want to illustrate how you can tell skew data from this. Does anyone need this up longer? If you do, say so. I'm going to come over here and sort this. I'm going to clear that selection. I'm going to sort by shoe size now. And we'll do descending again because I want to see those values past the 15. 15 was my upper fence. So I want to see shoe sizes. I got only a single shoe size above it. So I'm going to only have one. Oh, look at that. On the, it thinks that this is the age one. So it's showing me where that person shows up on the age. That's kind of neat. That's fun. Let's take a look at doing this now with our box plot. We're going to go graph, box plot. We select shoe size and we make sure the options are turned on. We click compute. And let's see how we did. Why do they keep going down by? I think they keep dropping down to the next lower value on the upper fence, and I'm not sure why. But they've got the outlier marked. It is the shoe size at 16. Theirs looks similar to ours. So I think we did a good box plot. So if you want to, if you're looking at a box plot, let's see, slide the camera. There we go. Work smarter, not harder. If you are looking at a box plot, In fact, I think I want to bring up both box plots. The one I have for shoe size, and I can bring back the one I have for age. Have those up on the screen. So identifying skewed data. The first thing to note is one whisker is much longer than the other. This is a dead giveaway. That's the first one. We'll call that A. A is a dead giveaway for skewed data. Sometimes they don't look longer though. Like the shoe size isn't really longer, and I would say the shoe size data is not skewed. One outlier doesn't make it skewed. 7 outliers out of this many doesn't make it skewed. The long whisker right here makes it skewed, and notice the boxes, how they're different. On the age box, the middle line is not in the center of the box. So that might be when the whiskers don't indicate it. Where does the median line lie in the box? If it's way off center, this is also another indication of skewed data. And why is that? Remember, each of these represents a quartile. Let me change color. This is 25% of the data. This is 25%. This is 25%. And all of this is 25%. Those aren't bad 25s for a mouse. So looking at it, if I'm gonna like I can get an idea of what the histogram looks like just by looking at it. Like if I have, let's see, I know Q2, there's a lot of data in a very small range because the box is narrow. A narrow box means a taller box. So that might be my Q2 all by itself, or the 25 to 50%. Q1 isn't much narrow or wider. It's a little bit wider, but it might be like I need to have this same amount of area in an area that maybe comes out to maybe here. So maybe I'll have like a box like this and a box like this. So this is like the 0 to 25%. And now I have a sprinkling, like the next 25% to the right, it's got a good size. It goes out maybe, it's almost like maybe 4 times as wide. This right box over here is maybe 4 times as wide as this left box. So I don't know. Let's see. 1, 2, 3, 4. I've got another 25% of the data. I need to have the same amount of box area in this region. So maybe I have something like that. And then I got a couple really short ones. And these represent 50 to 75%. And then Q4 has got a long range as well. There's going to be some boxes out here like this. They go for a while. And then we'll see just like little tiny boxes at the end for those outliers. That's what I'm guessing the histogram is going to look like. I'm going to plot it real quick just to check. But I'll let you finish drawing that first. If you need it up longer, let me know. I'm going to go do the histogram. I'm going to graph histogram. I'm going to do shoe size. I'm going to let it just choose it on its own, the bins. I might need to adjust the bins to make it look like it. Oh, wait, this was age I'm looking at. My bad. I'm like, that doesn't look anything like mine. What the hell? I was looking at the age. This is the age one, so I want to do age over here. Kind of close, right? But I got that from looking at the box plot and looking at the size of the boxes. A narrow box means a bunch of tall data right next to each other. Wider areas, like the end lines don't matter. It's the distance from here to here makes up the final box. And here to here, well, wherever the min is, that is the min. So there to undo that one. That part makes up the first box. So like I need to have very little over here on the left, or quite a bit over here on the left, and on the right it needs to be spread out over a large range. So it's spread out over a large range here, whereas we got the narrow box here is got a bunch of data clumped together right here. How is this doing it? It's doing 5-year brackets. I'm going to start. I'm going to edit this to tell it to start at 14 and do a width size of, let's go with, let's see how 3 looks first. Now it's starting to look more like my picture. If I make it look like a 2, even more so. Looks kind of like what I did, right? I guessed all that just looking at this box plot right here. Not that one. The other one, the good one. Where is it? Based on the width of the boxes. So the boxes can give away a lot. The whiskers give away a lot as well. So that's how you can tell skewed data. I think that's all we really need to say for this section. We will start chapter 5 on Thursday. We're skipping chapter 4 for now. I'm going to go back and do it. I don't include it on the midterm. So I do it like near the midterm, like either right before the midterm or right after the midterm, but it's not on the midterm. You really only need it to see stuff that we're doing in the later chapters. It's some graphing tools. And I think we're good for now. Is there any questions? So today we covered the z-score, which is x minus mu over sigma. You kind of need all of these three values to do it. You need that value, and that value to calculate it, and you're usually given it. Then we did the 5-number summary, which we just did, and box plots. I see a chat thing. Let's see. All right, we'll do that in a little second. Oh, Caprice, I see your question. We'll do it in a second. One other thing, if for the z-score, if you do not have the mean and the standard deviation, remember you can calculate it in StatCrunch. If you've got the data, you can calculate it by clicking mean and standard deviation. So you can, that's my mu, and that's my sigma. So remember, you can calculate that. And there we go. Okay. So, Caprice, do you want to share your question out loud, or you want to do it after class? I don't want to make an assumption.
After is fine.
Okay. I will stop recording. If there's any other questions, we'll call it a wrap. Oh, shit, you're the only one here. Let me just stop recording. Oh, almost click end. Don't want to do end. I need to do stop recording, and I need to hit record.